Hello, bonjour. Good to see so many people here. Glad to have the party and all that fun stuff. So we'll try to make this thing. But we got to talk about our failures here today, which is not something you see mentioned. We did kind of an engagement, and as the slide says, we messed up quite a bit, and we have enough to talk about it. So about us, we're Irdetto employees where we were at the time, and we do CTFs together. I'm Colin Dewinter. I was born in '94 and haven't used my life to the greatest capacity, so I don't really, still bad at everything. Jonathan Beverley has a specialty in static analysis and reverse engineering, and Ben Gardiner, on my left here, has a specialty in the hard way, which is doing things the hard way, and hardware as well, yeah. Just to give you a rough idea, it's 45 minutes, of course. We're going to talk about just through our competition that we did, the help we got, stuff we innovated, things we failed, of course, based on the other slides. That is quite the majority. That's a lot. So we'll talk about that a lot, and then we'll talk about the times it wasn't awful, wasn't terrible, didn't suck, and that's you know, the little bit when we need a little lightening up in the tone of the presentation. And then we might have some time for questions at the end if we're finished a little early. So this is the RHme3 challenge board. If you've ever seen a CTF challenge board, it looks similar to this. These are approximately, there's about 13, 15 challenges? 19 challenges. This entire CTF took place over a 4-month period. We were granted, somehow, we managed to get about a month and a half off of work to work on this. We got to give props to our employer at the time. I don't know if we'd ever get that type of stuff up again. And this is a little bit of the competition timeline. We're going to be jumping around from place to place to make sure this is keeps with our narrative of just failing hard and failing often. But just to help you guys out, you're going to see this in the top right corner of the screen as we go along, just because as we did the challenges chronologically, it doesn't match up with how I want to tell this story. So we've got 3 main sections of this. There's a pre-qualifier that you had to do for the RHme3. There was about, you had to do a pre-qualifier, you had to do that, and then you would be entered into a thing with 500 teams, which you'd compete for the entire 4 months. And then we completed it, and we have this lovely section at the end that is unbearable smugness. So that is just an unjustified sense of accomplishment that we carried with us, and we still carry it with us a little bit today. And it's funny because we didn't actually win, we came 3rd. So that's not even the first loser, that's the second loser. So this, a little bit of the themes of what we want to talk about. We want to talk about that failure is part of the process. When you're doing stuff that you've never been out in, you're outside in your comfort zone, you're going to fail, and that's okay. We want to talk to you about use outside resources. If you guys were on the boat yesterday or doing any of these other activities or just getting coffee, you know, people here are very friendly. They really want to talk about, you know, what interests them and things along those lines. So really leverage that when you're trying to do something that you're maybe not familiar with. And finally, we use the term Jugaad innovation. That is, I think, an Indian term. We've got just means hack it together a little bit. So in this case, we have a motorcycle tire made out of boots. Should work just as well.
Well enough.
Well enough, yeah. Use outside resources. We mentioned this a little bit. People love talking about things that they're happy with, and people also love talking about themselves. A little bit of case in point here, and maybe other stuff along those lines.
Think about that boat you were on. Think how much skill was on that boat. Think of what a small fraction of that skill you were. If you could leverage the skill of the people on that boat, you can solve almost any challenge in relatively quick order. You talk to many of those people. Talk to them again. Ask for their help.
We have a very special example of this. We had Ben. You worked on a reverse engineering challenge, which was one of the things during the 4-month challenge.
Yeah, I just wanted to finish one challenge that was reverse engineering, Jonathan, but you wouldn't let me do it, would you?
Well, I was too busy finishing the reverse engineering challenges.
Yeah, that's good.
Thanks for that.
I did leave you one, though. It's that red bar that starts at the beginning of the competition and ends at the end of the competition.
So I kept telling Jonathan, don't solve this challenge for me. I just want to get 100 points on the board in reverse engineering. And that red bar is spanning the entire length of this competition. When did we come up on like the very last day? And I was like, fine, I can't do it. I'm too busy doing other stuff.
It was noon on the last day when you said do it, and it was 3 on the last day, 3 p.m. when I did it.
Yeah, so he actually just did it on the last day. So we have a lot of speciality here, but still everybody's got their strengths, and we should always play to that. As well, we were able to leverage some of our coworkers' experience. We had a few people who worked in kind of white box crypto and some other AES implementations. So we were able to look at these for some of the side channel analysis, which we were pretty green on. We had had some experience with, but nothing super practical for the most part.
We were given like a half-day, here's what side channel analysis is course like a year before we started the challenge. That was all we knew.
Yeah, it was about a one level up from reading the Wikipedia summary. So any help is better than no help. We got a little bit of help from people just from all over, just from asking random things. Sometimes even a rubber duck can help you if anybody's ever tried to debug anything on code. We were shipped an extra board by a gentleman who was also in the contest and helped us out a little bit with that. And we also got some assistance on verifying what we thought was JTAG, but turned out to not be the exact case. Yeah.
You skipped over Colin O'Flynn, and I want to mention that guy.
Yeah.
He's the guy responsible for the Chip Whisperer project. He's really friendly and outgoing, and he would love to help you side channel analyze things.
Yep. So people don't know everything, but everybody kind of knows something, and so you can just use that to your advantage when you're in an instance where you're not familiar with how you should get things done. So let's talk a little bit about that Jugod innovation, that little motorcycle made out of boots. If you don't understand the problem and you get the flag in a CTF, how many more points do you have than a person who does understand the problem and gets the flag? The answer is you have the exact same amount of points. These are just about hacking it together and getting it to work. It doesn't, you don't need to understand a system 100%. You can understand it 50 or 60% maybe, and some sort of thing along those lines. Part of reverse engineering is finding out what's the 1 or 2% that's the most important part of the application that does crypto or does secrets or does assets, and completely ignoring the rest of the stuff that's just like, oh, this is just UI stuff.
Yeah, so this particular challenge was called Back to the Future. It's a little bit of a hint to what's going on. Metaphorically, there's this car dashboard. The physical board we had a lot of CAN and automobile technology built into it in the hardware. And this board had a pair of CAN controllers that were talking back and forth. And you needed to convince the central unit that the car was going at 88 miles an hour and the engine was running clean. Engine lights are used on cars to indicate almost every error that happens. That's why an engine light turning on means go to a mechanic. They can figure it out. It doesn't tell you anything other than there was an error. So all I had to do was make the car look clean and be going 88 miles an hour. I get a flag. There were two messages that seemed to control this. One from the engine saying things are good, and one from probably the axle or the drivetrain saying that it's going 88 miles an hour. I could make it clean. I could make it run. And if I tried to do both, I got engine errors. And I was tuning it. I was tweaking it, and it was like, everything's good. Oh no, there's an engine light, everything's good. Oh no, that's too slow, everything's good. And just did this, and this, and this, dropped a flag, went back down again. I kept it live for no more than 5.5 seconds, and I needed it up for 5 seconds. That was it. I asked them afterwards, and they said it was deliberately designed to be asshole. There was no way to actually keep it clean for an extended period of time. Getting it to stay clean for a whole minute was virtually impossible. And anyone who tried was stuck forever.
And so this board that we were talking about, that was something that was shipped to all 500 teams, and you'd load the challenges on top of it. And it actually came with this specific type of instruction set, which is AVR, which is what you'd use if you were working on Arduinos or something. And we had to create our own reverse engineering module for it. And this represents my attempt at attempting to make.
It's really good if you're trying to make a RHme chain. It just returns all over the place.
Yeah, if you this is what the disassembly looks like, because I tried to write my own macro. Very good for return-oriented programming, and I didn't even know you could return 2 registers at once. But here you go. And we really had to dig into this because the current tool structure didn't exist for AVR at that time for some of the disassemblers we were using.
So we didn't use Colin's module. In the end, it really wasn't very useful. Sorry, Colin.
The learning was useful.
The learning was useful. We took some of the machine-readable definitions that Microchip provides for the AVR and actually created a microprocessor configuration module. And then we ran into a whole bunch of different problems with XMega because it actually puts the register file in the memory map and the other types don't, which ended up being a problem when we first reverse engineered. But then after we set it up, we had the advantage that if we renamed areas in memory, they would actually also rename the registers. So we got to have nice ZL, ZHs, which you see here, and normally you don't get to see the pairs of those.
And the Z plus, which is actually the important thing. All the registers here are what? They're 1 byte wide?
Yeah.
And
Yeah.
it's got 2 byte addresses. So there's a couple magic registers. ZL and ZH are 30 and 31, if I remember correctly. And if you want to do something like load from a location in RAM, which is the last instruction up there, it reads the location from 2 registers at the same time.
Exactly right.
And this let us and IDA easily see how those all work together.
Precisely. So we actually found a blog post by a Cisco team from RHme3 where they just did the simple thing of taking any sequential set of instructions that use 2 pairs of loads and squishing them together into a pointer, just assuming that would be a cross-ref out into data space or code space. And doing that dumb thing actually worked. So they didn't ever publish the code, but we actually published all of this stuff on GitHub. So if you want to do some Xmega code, you can now do so with Xrefs. It's nice. We also had a look at...
I want to mention the 10, 1337 there. You notice that the pointer isn't actually pointing to the 1337 that the registers are pointing to? That's because ROM and RAM are mapped, have independent addresses in this Harvard architecture, but are mapped into the same address space. So that's a synthetic adjustment made by IDA so they can coexist in the same address space.
That's right. They put the whole other space just 100,000 hex up.
That's how hacky some of this stuff was, but it works really well.
Speaking of hacky, we tried to get a bunch of signatures to match, found out that flare and flirt will not work with Harvard architecture, separated address spaces, it just will never go. And we had some help from the IDA people and they basically said, nope, just will never work. But it turns out that bindiff, because of the way it has an intermediate language, would do matching. We were able to look at previous binaries from RHme3 and match, a good portion of them to get all the library functions right out of the box. Useful.
Yep. And on top of that, once we reversed one binary due to code reuse, we had most of the other binaries from it for free. This also references our talk to people. Ilfak, the guy running Hexrays and IDA, very friendly, very helpful.
Yeah, super helpful guy. So all of that is published on GitHub. It has other stuff too, like a scripted setup for doing loader loops and getting data copies into memory. And it even identifies stack variables, which is something that none of the plugins will do presently. So if you want to get some Xmega reversing, please go use our plugins.
So speaking of the other half of the infrastructure, on top of being able to reverse AVR, we need to be able to do side channel analysis. This is the setup we eventually went with after a whole bunch of trial and error. The important parts are those things. That's our picoscope. That's a battery pack, which is the stable power source. When you're doing power analysis, you do not want to be running on the mains. That moves a fair amount. You absolutely positively do not want to be using a USB port on a desktop. The power things on those are incredibly unstable. That detagulator in there is a $285 transistor. Yeah. It just takes 2 lines in and puts 1 line out. It's really that dumb. And that board in the bottom left with all the wires going into it, that is the target board. There's one other thing that's hidden in the middle, and that's our illegal USB cable. That's a split data power line. So the power from the board and the detagulator are going into the battery pack, but the data from the board is going into the desktop. It turns out that they were close enough that they could pretend they had a shared ground and things worked out. This allowed us to have the isolated power on the target systems, but still have live communication between the two so that they could actually talk to each other. We were absolutely blessed in this particular case. Because we had coworkers who did side channel analysis professionally, we could borrow their riskier inspector license, which meant we had $30,000 worth of software to throw at this target. And we got to learn what all those graphs on the screen are. The one on the right that's hidden is a power analysis. Each one of those thick vertical chunks is a single round of AES. The big thing on the left is an autocorrelation plot, which shows what it looks like when you compare the power to itself, makes a nice big grid. And again, we're talking rounds of AES, fake rounds actually, mostly in that particular picture. But the point is you can clearly see the structure of the program just written out there in the power traces. Want to talk then?
Yeah, I mean, we really wanted the Chip Whisperer to work. Colin O'Flynn is a super nice guy, but at the time that we were using this thing, it was migrating from 3 to 4, and also the Python split was happening too. So we ended up writing something in 4, having it not work, trying to backport, and then having that not work because dependencies weren't available. We also ran into a problem with the FPGA where you're trying to do glitching, and the FPGA would actually lock its one-shot. Like, I love this project. I wanted it to work. Apparently this stuff is resolved, but it was just a case of like, this thing just wasn't working for us. Too bad. Move on.
6 months earlier or 6 months later, it would have been the right project to use. At this point, at this time,
Yeah.
just a big pile of no. This is actually the thing that let us win. We got through 2 of the side channel analysis program problems, and as far as I'm concerned, that's a win for us because we didn't know how to do it when we started. JLSCA, I like to pretend that stands for the Justice League of Side Channel Analysis, but it doesn't. It stands for Julia Side Channel. And it's great. It's this really bizarre kind of scripty, kind of C language that lets you do all sorts of math operations natively. But it was written by mathematicians, so yeah, those are Unicode operators in the middle of your code, because the caret has to be saved for exponentiation. You can't dual purpose that for XORs. And then there's one other really weird thing here, which is that if everyone knows anything about crypto, there's no reason ever to add 1 to a value that's going through an S-box. But I have to for this code to work, and the reason for that is that arrays start at 1. I beat my head against a wall for a month over arrays starting at 1. There's a reason we mock it. It's terrible.
Brute forcing. Okay, sure. So we had a challenge called key fob, and all they told you was that you had a scan chain, and you had to figure out how to give the right response to a randomized challenge that this chip would give back to you. And after, you can see the timeline up here. It took us, 3/4 of the overall time of the challenge to figure this one out. And we just had to basically kind of fuzz this scan chain that was implemented in software. And eventually we figured out that, there's a particular bit that you set when you shift it in, and that tells it to send back a challenge to you. And then you have to set another bit to say, okay, here's my response. You send that in, and if you get it right, it will give you the correct flag. If you get it wrong, it just kind of hangs, and you have to reset it. So what you're seeing here is a timing diagram that was hard won by us just kind of like banging on this chip again and again, and a lot of false starts too, including JTAG, which
a lot of false starts.
Wasn't JTAG. But eventually when we figured out how this challenge response kind of worked, we didn't have enough information to even know what the algorithm was. We just know it was like a number this big, and you have to send a number that big, which is a huge space of what possible algorithms you could possibly use. We figured it might be AES related because a lot of the hardware acceleration is AES. But that still meant that we had hours upon hours upon hours of brute forcing to execute. So I have pictures of me brute forcing this chip in a box setup on a car. That's in the passenger side seat of a car. That's me on a plane brute forcing. This is me boarding a plane brute forcing. The attendant actually wanted to hold it for me. She said it looks important. And I was like, no, this is too important for you to hold. The guy behind me was not cool with this. He didn't think it was a good idea at all. A couple of months later, I actually have a friend in the aviation ISAC, and she sent me this text message exchange you can see here. And she says, did you board a Delta flight with a box of wires and blinking lights? Are you stupid? And I'm like, well, yes and possibly yes. And they're telling me that they were trying to get me banned. The next day, of course, I found out that someone else was trolling me, and they got her to contact me. So luckily, I'm not banned from Delta flights, because that would be a pain in the ass.
Well, the thing was, they forgot to tell him he was being pranked. They just kind of forgot. They told him he was possibly on a no-fly list, and he had customer visits coming up, and he had to do his regular job. So it's a very stressful 4 days.
Yeah.
And then they got back, and he asked her about it, and how's that keeping me off the no-fly list? And she's like, oh, no, that was a joke. No, you're fine. But they just forgot to tell him.
They got me pretty good, yeah.
This challenge. So, keeping in the theme with brute forcing, sometimes you just have to do things the hard way. Sometimes you're facing a challenge, you think there's cute solutions, they don't work, you try the things, they don't work, and you just look at it and be like, okay, I have 2 kilobytes of binary, it's not actually that much binary, I'm going to literally hand lift all the assembly to C by myself, and then given that C and an effective emulator, I'm going to debug it until it is bug for bug compatible with the original program, and now I can work with the C. The emulation environment was too slow. It did not work well enough for me to be able to debug this problem in the emulator, so I ended up debugging it in C. And my C actually worked flawlessly eventually. And I was able to find the problem in the code that way. So it was a method I knew would work if I put in the day and a half of solid work to lift all that code.
So just in keeping in mind, which is kind of getting it working, this is, as we said before with the chip whisperer, it actually locked on. So for anybody, it was a transistor designed to push a lot of power through itself such that it could kind of short the power of the system we were working on. So if you stick that into the on position, it gets really hot, and it gets really hot really fast. And you had a glowing red resistor that he just kind of ignored, and you'd just be sitting there and you go, oh, something's smoking, and it would be a resistor. We actually had to rebuild our own transistor, and that one on the left there is taken out of a graphics card.
VGA.
VGA, an old VGA. So that was able to pull the power down to 0 volts in like a couple nanoseconds, something along those lines.
Bang.
So as you can see, we just have to make, and then on the right side we have kind of this wire box that we created, and things don't have to be pretty, but they do have to be magnifique. You know, I'm in France, so I'll do that.
Yeah. That is pretty to me.
Yeah, and these are just ways that we kind of set up this box and just this amount of wires and how we had to manage it in this situation. If you're familiar with the picture on the right, that is something called pin lifting, where you desolder your chip in certain spots such that we could get a voltage read across the power lines of the thing we were working on.
This is possibly the most important and hardest part of the side channel setup. You can measure the differential across that giant resistor on the left, which is so much easier than trying to do it across the pins that your probe literally can't fit around.
Yep.
So do tough things when you need to. Sometimes you need to hand lift C. Sometimes you just need to brute force on a plane and then never ever get on another plane again. And
Ugly and inelegant and gets you a flag, still gets you a flag.
Yeah, still gets you a flag.
Flags. Yep.
Flags.
But that really wasn't what our thing was about, right? Our talk is RHme3 hacking for failure. So let's talk about failure.
This section's going to be a lot about me.
This is,
A lot of fail. So we had to do a pre-qualifier, as we mentioned, and you guys were all busy, and I really wanted us to get into the riskier hack me because I just thought it was super cool. So this is August, and I'm on vacation with my family, and they're asleep, and I'm like trying to do these qualifiers. And you can see here, this is an execution trace in the green and the red from the side channel Marvel toolkit. What it does is it takes the little reads and the writes, and then it does just correlation analysis to try to find like an AES key. So it did reliably find an AES key. You can see it right here, and it had a high confidence. But I kept submitting it as a flag and just going like, what is going on? Why isn't this the flag? The confidence is like right up there. And because I'm stupid, I never thought that this could have actually just been ASCII. And so we actually missed the qualifiers, not just because of this failure, but partly because of my idiocy, unable to convert to ASCII. So failing. You know what? Fail, move on, fail at something else.
So the autopsy challenge, the auto side challenge, was the third of the CAN car hacking challenges, the hardest one. And I spent an awful lot of time on this one because, well, you see, it had weird backdoor capabilities, and I figured out how to open the back door. I figured out how to get through the back door. I couldn't get it to drop the flag. I eventually put it into the emulator, figured out why it was broken, figured out how it was broken, patched it live in the emulator, got it to run through. It dropped a hex string. I'm like, great. I submit that. I get nothing. I got nothing because someone else, instead of doing that, had reported the error and they'd fixed it. And when they fixed it, it automatically cycled the flag, so my flag was invalid.
Ouch. Oh, talk about this one, Jonathan.
Oh, I get to talk about this
Oh,
one?
yeah.
I talk about how I failed?
Yeah,
Okay,
this is
so
failure.
this was a 250-point challenge. The challenges ranged up to 750 points. Despite being 250 points, it was possibly the hardest challenge on the board. 2 weeks full-time reverse engineering. Once you had the exploit, it took 30 minutes to deliver the exploit to the target board. This is not remote. This is not something fucked up. This is direct serial access to the board, and it still takes 30 minutes to get through the exploitation path. After you make your exploit attempt, the board will then spend 6 hours processing. This is a busy loop with a counter so big they needed to add another variable to track it because it would have overflowed. And this nice guy wanted to take the thing away from more brute forcing over the weekend, and so I let him take it, but asked him to check the console. He carried it home live in his trunk. He pops it open, and nothing. Right there, pasco.log, nothing. And then what did you do?
And then I was like, maybe John didn't like flush the buffer of the serial port.
Yeah.
Flag.
Yeah, so we had it sitting in there, and we almost lost. We would have thought there would have been something wrong with it, so we would have lost maybe another couple days plus another, 6.5 hours getting the response back.
Glitch up. So we did actually get into some glitching towards the end. We never successfully glitched one of the targets. You can see here a power trace showing like where the LED turns on, what a normal execution would be intermixed with, what happens when you start glitching one of the rails during processing. The game here was to actually find the right place to glitch it to change a variable to set a mask to clear so that you could change execution and then get the flag to drop out. What we did manage to do was actually do like an instruction glitch and skipped one step. So it went down the right path, but it never cleared the flag. So what you see here is, after a couple days of glitching, it says, congratulations, your flag is FFFFFFF. So all we got was the mask out, and this was after multiple days, to which I replied, no.
Yeah,
we had an hour left or something.
Yeah, just to give it a little update on the X's. The X's told you how many parts of your answer that you put in were wrong, and that was constantly changing. And so we were trying to glitch the power while it was checking how many were wrong, such that when it loaded it, it would glitch, and then it would load it as a 0 instead of actually the amount that it was. So then it would skip over to the wrong one.
Yeah, skip wrong.
Skip wrong still wasn't right.
Oh, man.
Yeah.
You get to relive this
No,
one, Ben.
I don't want to relive it. You talk about it.
Go on.
I don't like talking
Yeah.
about this one.
So there was a challenge that was just called
Phonic Frenzy.
Phonic Frenzy. So this is it. You would connect some of the wires to it, and it would tell you in a lovely, lovely voice. It sounded like a Commodore 64 voice modulator exactly what was wrong with your program, and it would say that back to you, and you'd have to reconnect some of the output wires to the input wires, and it was just a loop-back system for the most part.
Yeah, should have been.
Yeah, and so we don't have sound. I'll bless you guys that a bit.
I don't want to hear it anymore. So
Yeah, we heard this. This is a table that we created, though, and this is all the wires connected to all the other wires. So each time we did this entry in a table, you had to listen for about 30 or 40 seconds to welcome to the infotainment center. And it would just keep going, and then it would be like, incorrectly, correctly. It would just be this absolute pain. And we get the messages, we mark down each message.
And then Ben was like, I've tried all possibilities, I've graphed it out, this is no solution. Obviously I've made a mistake, I'm gonna go back and do it all again.
Yeah. So he completed
I
it.
would learn.
He brute forced again, and he brute forced 2 entire tables worth of the things. And the problem came from
Fundamentally,
this.
this graph, do you see the A pins on the bottom left? This is actually a top-down view of the board and where the pins on it are. You have to connect the A pins on the left to the D pins on the right. And by doing so in the right pattern, you make the thing think that a module has been attached to it and should it unlock additional functionality. That functionality be dropping flags. So Ben here tried every combination of matching the A pins to the D pins, but he didn't need to move the A pins. What pins did he need to move? Was it the PA pins?
Yeah, it's this little guy over here, which on the silk screen had nothing to do with A at all, but on the schematic was obviously A. So I just needed to actually read the schematic. Yep. I'll never learn my lesson. I'll keep doing it.
Tell us about the Jetagulator, Ben.
Sometimes you fail because everything looks like a nail when you have a hammer. We had a Jetagulator. You saw it earlier. I love the Jetagulator. And when we read the car key fob challenge, it really sounded like this was JTAG, right? They said, you have a scan chain, interface with this scan chain to get the flag. Okay, scan chain, JTAG, obviously, right? More brute forcing. We put a delay in this because it was software emulated scan chain, so you had to go slow, and we just left it overnight, scanning and scanning and scanning, and this thing would report that it was self-destructing like you wouldn't believe. It didn't matter what we tried, this was not JTAG. So that was not my fault. It just wasn't JTAG.
Yeah, well, spent an awful lot of time finding out that it wasn't
my
JTAG.
fault.
Yeah,
Okay,
yeah.
I'll take that. That was me for like days.
But that failure wasn't really your fault.
Well, I think we just said it was my fault.
Oh, yeah. But car key fob in general wasn't your fault.
It wasn't my fault.
No.
No.
It wasn't his fault,
Not
guys.
my
It
fault.
wasn't,
Not my fault.
yeah.
Moving on. So this is another terrible side channel analysis lesson. It has to do with the confluence of the real world and the CTF world. Our friends who work with us who do side channel analysis, they have to deal with real world systems, which are noisy, which frequently have hardware defenses. Side channel analysis on a multi-threaded system is always harder. And so every time we told him we couldn't manage to get a signal out of this thing, he said, take more traces. At one point, I was spending 16, 18 hours just capturing traces from this board. I ended up with 250,000 traces. It was like 10 gigabytes of data that I'd extracted from this board looking for a signal. When you have 25 million traces, 10 gigabytes of data, trying to do an elastic align, which is like this complex process where you try and figure out what the exact lineup between these things are, it will take 2.5, 3 days to execute. We had a like octo-core Xeon that they weren't using at that moment that we could borrow for a week or 3. And it was seriously almost 3 days of just raw processing. And it turns out that elastic align was not in any way helpful, and that those problems could be solved with less than 1,000 traces.
So when you're doing stuff like this, you'll fail. It happens. It happened to us, and it's also varying ways. I'll look over here then. And that's just kind of the thing of it. But the thing about failure is you fail because you're trying to do stuff that's new and different, and when you actually end up doing it, you get to enjoy the eurekas of your moment, and that's kind of to bring stuff up on that. Most specifically, as an example, would be our car key fob.
It was not my fault.
It actually was not his fault. I know we put that up there for a second. What had actually happened is they had given us another wrong version, and what happened was you sent them the scripts.
Yeah, we wrote scripts, and they covered every single possibility of brute forcing. We just said, look, here's the scripts. Where are we going wrong? And was it about like 4 days later, they're like, yeah, we made a mistake.
Yeah.
So it turns out that all the firmwares we were shipped were individualized on a team-by-team basis, and there was a bug in that process. So as a consequence, the master version that they were testing worked flawlessly, but the individualized versions that they shipped to us were broken. And they didn't go back and test the specific individualized version that shipped anyone until this point in the challenge.
Yep. So all that plain brute forcing was in vain. Well, we got the gold star. We got the gold star.
I don't actually know what the solution is to this day, so maybe it wasn't in vain.
Yeah.
Imposters. This was a really fun side channel analysis problem. There were 16 rounds if you looked at the power trace. When you hear there's 11 rounds in normal AES, when you see 16 rounds in the trace and there's 11 rounds real, you think there's 5 fake rounds, right? Unless you're Ben. And so I spent a very long time reading the literature on fake rounds to hide and defend against side channel analysis, trying to figure out how to move them around. What was it eventually, Ben?
It was hardware accelerated AES, John.
Yeah, it was. So every one of those 16 rounds was an AES computation all by itself. It turns out that hardware AES is actually faster than a single round of software AES. Yeah. So, I mean, it took us another month to sort out Ilya Kishkakov's attack and make it actually work, but at least we're on the right channel at that point. Speaking of spending a month on working, this was me at like 9 p.m. in the office. No, this one up.
Oh, yeah.
That notepad on the right is the genius solution to it. I was basically running around the office cackling Eureka at 9 p.m. and these guys were asking what's up, and I like vague tweeted that image to them and then went to bed.
Yeah. We were like, yeah, it makes perfect sense.
Makes perfect
Good
sense.
job, John.
It turns out that you need to know the relationship between the order that the AES is happening in. You need to know which block is processed after which block. And for optimization reasons, they'd shifted from linear to mixed column order. It doesn't make any sense unless you know side channel analysis. But the point is that they've made a really simple change for optimization reasons, and it broke everyone's attempts to do hardware and analysis on hardware AES. And other instances. I mean, like, so you have to remember this is a 4-month-long challenge. We got 17 flags. So I'm not doing the math off the top of my head, but it means like 7 or 8 days between flags at the very least. So you need to maintain momentum, you need to maintain morale, and that means you need to celebrate your victories and enjoy it, because you're going to spend long periods without doing very much at all.
If you've ever done a CTF and really struggled to even get one flag, and that's like a weekend CTF, imagine that being, because there was a lot of tooling up at the very starting, so imagine doing that for being in a CTF for 3 or 4 weeks and not getting a single flag. As a summary, we are unbearably smug. If you've met us, we were here all week, so I mean, maybe some of you know already. And we only came third, and we've decided to make this a talk and talk about how much we lost in the entire thing.
Somehow. Thank
Thanks.
you.
Yeah, if you have any questions, we do have full write-ups.
Yes, I did the write-ups. I finally
Yes.
finished my write-ups.
Yeah.
In a previous version of the talk, we were getting on and did actually finish that write-up, but that's all up on our GitHub. It's very detailed, and we go into a lot of times. If you guys want to check out how we kind of started from an elementary understanding of side channel through more in-depth on the AVR scripts that we kind of did, more memory in-depth stuff. And if you just want to see how, if you're looking to get into reverse engineering, ask some questions, or even after. I mean, there's one more talk after this, but come find us and we'll definitely talk about it.
I want to spend 1 minute shilling for my side channel analysis notebooks. Julia loves to run in Jupyter notebooks. So there are 2 fully functional Jupyter notebooks that you can run that will do side channel analysis live before your eyes. All the source code that you need to do it is nearby or part of the well-established JLSCA Julia projects. And the completed notebook is there, so even if you don't have the setup, GitHub renders Jupyter notebooks. So you can just click on the notebook, and it will show you the whole process with all the data from when I executed it. So that's a full live side channel analysis happening that you can just read through and see how it worked.
Totally.
Questions? Also, we have this, I don't remember the name of it, Slido thing that you can use to ask questions online if you wish to. Thank you very much.
Yeah.
Thanks, everybody.